I would like to welcome all of you to the second part of our meeting. The last time we have looked at contingency table. We were able to look at how to draw contingency table in the form of a heat map. Or if you don't want to do it in a heat map, in a normal write-up. Contingency tables are necessary when you are dealing with categories, groups. When you have a lot of groups in your data set, you can use contingency table to address a number of patterns and certain things. So we did that. Then we looked at descriptive statistics. We were able to show how to find a transpose so that it looks better than in the normal form. In the normal form, the variables are at the top. But in the transpose, the statistics are at the top. We're able to see that. And we said something about the mean and the standard deviation. Who can tell us? Who can tell us what we said about the mean and the standard deviation? We made a comment related to that. Who remembers? Those of you who have backstage me, that you already have first class, you are the ones I will expect to communicate and share your knowledge. Otherwise, it means that you are doing chew and pour. So if you don't talk in the class, I cannot be helpful to you. Those of you, even though I've created a group for you, just to warn you, you can't just, I can't sacrifice to help you when you are not being very contributory in my class. So what did we say about the mean and then the standard deviation? Yes, Samuel.
Sir, we said that there is a relationship between the mean and the standard deviation, and when the standard deviation is lesser than the mean, that means the quantity demanded are equal or similar or quite related in size. And when the standard deviation is greater than the mean, that means the quantity demanded have vast differences.
Good. What do you mean by have vast differences? How would you explain that to a 7-year-old?
As in the range between
Listen. I said, how would you explain that to a 7-year-old?
Okay, so I'll explain to a 7-year-old that when the standard deviation is greater than a mean, that means that the numbers or the numerical figures you are going to see won't be the same, won't be similar, or won't be closely related. You see them to be having some huge differences. And when the standard deviation is lesser than the mean, that means the figures or the numerical figures you are going to see will be quite okay or will be quite related or similar.
Okay, very good. So we were able to establish these facts. It comes somewhere out in your eyes. So you have done justice to that. We also looked at the descriptive statistics across groups, and we did a lot of commenting on them. Then we gave a complete model of all the possible summary statistics you can get. So what I'm going to do here is I'm going to just be quickly asking you to tell me your mind about each one of them. First of all, the code is to run these statistics, ensuring that they are numerical variables. If they are categorical variables, you cannot find their statistics. Or even if you find them, it is not that meaningful. They won't be that meaningful. So let's start with the mean, median, mode. You know it. When the mean is the same as the mode, which is the same as the median, what does that mean? When you run all of this, you're going to get the results I'm about to show you. You see, I use the word print to get the results. I use the word print. Now, if I remove the print and I just write the summary stars, it puts it in a very nice table like this. Okay. See, it puts it in a very nice table like you see here. So that is also not bad to have it in that way. All right, so the count here refers to what? Quickly, let's try to clarify these things because these are very, very common things that you should know. The count refers to what? What does the count mean? Pardon? Yeah, Malaka. Yes, Malaka. Yeah, precious.
Is the total number of items in the data set.
Okay, so the sample size. What does a mean mean? That is easy. My question was, when the mean is the same as the median, the same as the mode, what does it mean? What would be the value of the standard deviation when the mean is the same as the median is the same as the mode? What is the value of the standard deviation at that time without accent chat or Google?
Zero.
Why? Why?
But when it is the same, the data set is more or less perfectly distributed. So it will be that will cause the median, the mode, and the mean to be the same more or less. So when you calculate the standard deviation,
What is the managerial implication of that? What does that mean? When the mean, the median, and the mode are the same, leading to a zero standard deviation, what is the implication of that to management? Who can tell us? What is it? You remember the HOD today said that it's not just the calculations, but the meanings of the calculation. So what is the implication of that? It implies that the firms or the observations you are watching, they are the same size. That's what it means. It means that in this case, if it is a quantity we are talking about, they all have the same value of quantity. If it is a price we are talking about, it means that they are all having the same prices. That's what it means. So when the mean is the same as the median and the mode, that's what it implies. Okay. The standard deviation will tell you the dispersion. What is the coefficient of variation? And when would you need that? What does it measure? The coefficient of variation measures what? Is it a measure of the central tendency or a measure of the dispersion?
Dispersion, sir.
Why do you say that? Why do you say that? Or you're doing lottery? You should find out the difference. Yes, Malaka. I think Malachi, when you
how they varies from each other.
okay.
Yes, so possibly speaking at the variance or how it differs from each other for each single site.
Good. So the coefficient of variation measures risk, particularly in stock market. It measures risk. The coefficient of variation. You should know clearly the distinguishing differences between the skewness and the kurtosis. You should know how the interquartile range is calculated. You should know how the geometric mean is also calculated. You should know all of that. Okay. Take note. Who can tell me how to calculate the range? What is a simple calculation of the range? It's the maximum value minus the minimum value. That's the range. Maximum value minus the minimum value. So now let's quickly look at visualizations. You may do, in your project, you do these things. You do visualizations. Okay. And there are multiple visualizations you can do, but the major ones are the ones I want to show you. So there's a package called, there's a library known as Matplot library, PyPlot. Have you been taught that?
Yes, Doc.
Yes, Doc.
So what is that? What is it for?
It's used to visualize statistical data sets.
All right. So we use these ones to do some graphical interpretations, graphics. Graphics are very important. In fact, you need to have at least 6 graphics in your project. At least 6 different ones. Okay. So let's look at the first one and when is it needed? Histogram. Histogram tells you how particular observation, the particular variable is distributed. Okay. So how a particular observation variables are distributed. And sometimes we superimpose a kernel density plot or kernel density estimation on the histogram. Okay. So what do you use the histogram for? Who can give me a fair idea? What are you going to use the histogram for? Mainly speaking. Someone. Mainly speaking, what is a histogram used for?
Histogram is used to check for the comparison or the distribution when it comes to numerical variables.
Okay. So what are some of the things a histogram can tell you? It can tell you whether your entire distribution is what? It can tell you whether the entire, as you can see in our example here, it is scale. We are trying to check its distribution. It's scale. The histogram can tell you something about entire distribution. What are some of the things it can tell you? One, write it down. It can tell you whether the entire distribution is normal or is not normal. Take note. Whether the distribution is normally distributed or it is not normally distributed. I think you know that by now, what it means. If you don't know, raise your hand. That's the first thing. In other words, it can tell you whether the data in total are symmetrical or not. If they are not symmetrical, what are they?
Skewed.
Skewed. Okay. If they are not symmetrical, they are either left skewed or right skewed. Now, the histogram can also exhibit bimodality. What does that mean? And remember, the histogram can come along with the smooth kernel density estimation. The kernel density estimation is much better than the histogram, but they depict a similar thing. Okay, what does it mean when we say that a histogram is exhibiting bimodality?
So we can say that it has two distinct peaks or modes.
Exactly. When it has more than two, what is it called? When it has more than two, what is it called? Multimodality. Multimodality. Take note. So that is a histogram also with a kernel density plot. Okay. We are going to do that for quantity demanded. The other one, okay, so let's look at it first. Okay. Look at the histogram for quantity demanded and the kernel density plot. If you look at it carefully, what is the nature of the mode? You can tell us. What is the nature of the mode here? No. How many peaks does it have?
Four, two.
How many peaks does it have? As you can see, it has two peaks. Okay. And because it has two peaks, it exhibits that spirit of multimodality. Now, on the right side, you can also plot box plot, okay, of religion. The center of the box plot is known as a median. And there are a lot of things you can say about it. Let's start with the box plot. So as you can see here, the box plot is showing which one has the highest median. Kudicha.
Say Christian.
What makes you say that?
Because the number is between 200 and 220.
No. Be clear. Because what? Those of you typing, open your mouth and talk rather than type. Typing is not the best way of communicating on Zoom. Zoom teaching is bad because people hide behind the scenes. Some are not even paying attention. Somebody will put their phone somewhere and go and do something. So it is only when you talk here that I know you are listening to me, not when you type. So what can you say about this box plot? Which religion are the religious group are the highest consumers of gym-bitters? Which religious group are the highest consumers of gym-bitters? However, there's something. Even though it's Christians, because they have the highest, median, the median is a black horizontal line. Okay, there's something about them. Okay, and I'll put it here for you. The box plot compares the distribution of quantity demanded across groups, across religious groups. Okay, and you can see that the median is in the center. As you can see there, the median is in the center. Then the spread, the interquartile range, and the variability, they overlap. You can see that this blue color here, in fact, you could have used rainbow, to be honest with you. Okay. Let's see. Let me see whether you can use. You can change the color to rainbow. Let me try and see whether that will come. Or it is R that does that. Forgotten. Uh-oh. Let's try it again. You should be doing the same thing to yours. Me, when you use ChatGPT, I'll catch you. I'll catch you in the exam time. So it's important you are learning to run these things yourself. Yes. I was trying to add some bit of color. You know. And like I said, I don't know whether it's gonna work. Each time I try to run, this thing I'm not showing. That's all this. Yeah. I think it's the R that does that. Okay. So other colors will show. We just did some red here. So as you can see, this is it. There are a lot of things you can say. For example, we've indicated that the boss plot shows clear differences in quantity demanded across the religious group. Christians exhibit the highest median. Muslims exhibit the lowest median. So Muslims are the lowest consumers of aquatic. You can see that right here. Okay, you can see that the median for Muslim is around 150 bottles, whereas the median for Christians is over 200 bottles. So that's one thing you can observe. Okay, the Buddhists show the greatest variability. Watch it. The Buddhists, they show the greatest variability. When you look at the median is in the top 75% of the data set. So it tells you that there's a lot of disparity of variability in the consumers of aquatic when it comes to Muslims. It's possible that some are actually hiding that they don't take aquatic when in fact they actually take it. So that is why you can see that the median is in the top half of the data than the middle half or the bottom half. Okay. The next thing is what is known as quantile normal probability plot. Okay, the quantile plot. The quantile plot is done to show also normality, whether the data is normal, apart from the KDE, the kernel density estimation, and the histogram. This one also does the same thing. You just simply want the dot, the blue dot, to sit on the red line. That's it. For you to conclude that it is normal. If it doesn't, it means it is not normally distributed. Now, when you look at the kill, would you say it's normally distributed or it's not normally distributed? Quantity demanded. What would you say? Is it normal or not? Well, you can see right through the needle there, okay? Even though it might look like it's roughly in the center, it doesn't satisfy normality assumption. Okay, when you look at the tails, the deviations indicate departures from normality. And we look at that, there is a blue far departed from normality in the data set. So that is one thing you can use to determine the normality or not. And then, of course, we've said that kernel density will tell you the shape and the distribution, not just the central tendency, okay, the shape and the distribution. And in our case, there are two clear peaks exhibiting bimodality. Very, very clear. When you go to the histogram, it's clear. When you go to the kernel density, it's also clear there. Okay. Now, what does that mean? This bimodality, what does that mean in practical sense? And you should be able to explain this in your long essay when you are ever writing, and you should also be able to explain it well when you are presenting. You should be able to explain it. So it's not just to come and learn and pass here. It's to learn and make sense of what you're learning. So in this case, watch it. The bimodal shape will tell you that the quantity demanded may be generated from two different underlying processes or two different groups. That's what it means. Yes, there are three groups, all right, but it appears that two groups are the key one. They are generating most of the data. It can be that there are two different locations. As you can see, we have urban and then we have rural. It's possible that there are three religions, but only two of them are the ones from which the rest are, the distribution is being taken from. So that is one thing that I can tell you. Sometimes a time period, there are two different time periods, so you can tell us. But all of these are good, but they don't tell you whether the quantity demanded is normally distributed. Guys, who can tell me? If you want to check whether the quantity demanded is normally distributed, what do you do? How do you test? What do you do? What do you do to test? First, you need to test statistically. But what do you use to test? What do you use to do the testing? Okay, it looks like you haven't been taught, so it is known as normality. Okay, normality. That is what you use to do the test to check whether the data is normally distributed. You check for the normality. And there are several tests for normality. You have the Kolmogorov-Smirnov test. You have the Shapiro-Wilk test, and so forth, and the Sandalin test, several of them. But the key one we are going to focus on is the Shapiro-Wilk test. So apart from the visualization, we check this. The null hypothesis will say that the Q, which is what you are testing, is normally distributed. That's it. That's the null. So if you don't reject the null, then you're going to conclude that truly, the data is normally distributed. The alternative is say that no, the data is not normally distributed. This is a Shapiro-Wilk test, the test statistic. When you are writing your thesis, it will be nice to put in the test statistics in your chapter 3, which is your methodology. You put it there. You let the reader know that this is it. You are not just quoting things from your head. This is the mathematical formula, which is good. So the W means work, the name of the person. It was two people who propounded this. The good thing about this test is that when you are looking at it, it can help you to know whether the data is normal. The moment it is very close to 1, then it means that the data is normal, the test statistical. But if it is far away from 1, it is not normally distributed. So take note of the interpretation of the normally distributed. If the W is close to 1, now how do you define close to 1? Well, I can promise you that 0.8 is not close to 1. When it comes to normality, 0.9 is not even close to 1. 0.91, 92, 93 is not even close to 1. For it to be close to 1, it has to be something else. And that something else, it must be above 0.97 or above 0.96 for it to be close to 1. So we're going to do the test, okay? We are not using this Kolmogorov-Smirnov. All of them are powerful, but then we're going to just use the Shapiro. So you can see that in the first command here, I've commandeered the Shapiro, okay? And I'm doing a Shapiro test of K, which is inside the DF data. If you do that and you run, you get a result. The next run will give you the nitty-gritties of the result. And then finally, you will have the p-value. Let's show the result. So that's the result you see there. So looking at the Shapiro test, just looking at the test, would you say it appears to be normal or is it not normal? Is it normally distributed or not normally distributed?
It's not
Looking at
normally
it, what makes you say that?
because it's not above 0.97.
Very good. You can also use the p-value to determine. Who can tell me the extent to which the p-value confirms non-normality? Anyway, so here's the rule. The rule is that whenever the p-value is greater than 5%, it means that the data, the variable, is normally distributed. Write it down. When the p-value is bigger than 5, that's good news. All right. So the moment you see the 91%, you may be tempted. 91 is not very close to 1 at all in the Shapiro world. Okay. In real world, especially with a lot of data, W is supposed to be between 0.97 or even 0.99. Now it becomes more believable. Okay. The next important thing you would do, you have to do in your data preprocessing work is known as correlation matrix. This time we're going to use something called heat map to do it. What is correlation? Who can just tell us what is correlation? I would say there's a correlation between what you did and what is happening. What is a correlation? Yes, Sammy?
So, Doug, you are trying to find a relationship between two variables, whereby one is an independent variable and one is a dependent variable. And you are trying to explain that whatever happens to the independent variable, what effect is it going to have on the dependent variable?
No, you're trying, but then that is not correlation. Correlation does not look at effect. Correlation simply looks at the relationship existing between them. The relationship. Whether that relationship is positive or negative, that is a correlation. It does not establish causality. Yeah. There's a correlation doesn't mean that there is a causation. Write it down. Correlation is not the same as causality. Correlation is different from causality. Okay, so we're going to use heat map to generate the correlation matrix. Now, somebody said, well, how will I be able to know this code? Sometimes when you are here and you are doing it with me, you know. Okay. So now we are going to generate a correlation matrix for the appropriate variables. Why the word appropriate? Appropriate because some of the variables are categorical and we don't want to generate their correlation. The correlation we are generating is only for the numerical variables. Take note. I thought that you won't get that for categorical variables, dummy variables. There is no go and find out why you don't need the correlation for dummies. Why you don't need it. So look at the correlation here. This is a commando. Go through it one by one. The shape, okay, you have to rename the data. Tell it to give you the p-values. And the p-values are here. Okay, so when it is 1%, it means there are 3 stars. 5% means there are 2 stars. When 0%, no, 10% means there are, well, there's 1 star. And then 0% or 0.00, that is just what is known as a Nothing, empty. Okay. So I'm going to generate the correlation, but I want to generate the correlation to look like the Excel one. Of course, the first one, you cannot get it like the Excel one, but subsequent ones, you should be able to get it like the Excel one. So that's what I'm going to do. Okay. So you're going to generate this heat map, and then we'll show the left diagonal alone. We don't want to show the right diagonal. So we command heat map to show only the left diagonal, the lower one. And when you run it, you're going to get this beautiful result. Okay. So what do the stars in each of the correlation pairs tell you? What do the stars mean? You can see that here all the decimals have been brought. You should convert your final work to 2 decimals. You know, somebody is watching it like that, but the person is not thinking of. I have a series of questions. And of course, the last one will generate the heat map. So you can see that here you have a color to depict the intensity, but it also tells you the numbers. Okay. So what did this mean? When you look at it carefully, it means that there's a correlation among all the variables. That's what it means. In other words, the variables tend to have some relationship with them, the dependent variable. Earlier on, one of you said dependent and independent, but we don't talk about dependent and independent. We just talk about variables. Because you just don't know which one is dependent and which one is independent. Okay, so you should be able to generate this heat map. Let me see the answers of you have done it. The heat map. There are 2 ways of doing it. I've done all here for you to see. Abigail and Ponsa. Who else? Who else had done it? Jonathan. Who else? Samuel and Obed. Abigail. Who else? Okay. Got quite a few of you. So now that you have the correlation, you are going to address the following questions. Question number 1. Which 3 pairs of variables are perfectly correlated? You can raise your hand and tell me. Which pairs of variables are perfectly correlated? 2 pairs. 2 pairs of variables. 3 pairs. Okay. You can use this one. By the way, perfect correlation simply means that they have a coefficient of 1. And normally when they have a coefficient of 1, we don't even look at them. So you can see this here. In the table here, you can see it better. The correlation there. So which first pair is highly correlated perfectly? Which is the first pair? Who is cracking the code? Sammy? Nene?
Say P and Q.
No. Obed?
Yeah, dog, please, quantity and quantity.
Exactly. Then you mentioned the coefficient.
1.0.
Very good. Who can tell us the second pair? Adi, we are father.
Price and price, which is 1.0.
Good. Third one. Yes, Sammy. Yes, Sammy.
Doc, please, C and C, that's C and C.
Very good.
Yeah.
So when we say perfect, that's what we mean. Number two, which pairs of variables exhibit high correlation with the response variable? I'm telling you, these are our exam questions. Which two pairs of variables exhibit high correlation with the response? In this context, which variable was the response? Mhm. By the way, did you guys have class today?
No, please.
No, Doc.
You guys want to go and chill. Thank God it's Friday. So you want to go and chill.
Yeah.
Do you say yeah? So that I let you go and chill. If you want to go and chill, say it so that I let you go and chill.
No, please,
nah.
Doc.
We want to learn.
So who can tell me? Which is the response? The response variable is also the dependent variable. So which variable is a dependent variable?
Please, the price.
Why do you say that? You see the variables at the bottom. Yes, I mean.
So, Doc, please, the dependent variable is the quantity demanded.
Why?
Because the price would determine the quantity that will be demanded by a group of people.
Good. You're right. The quantity demanded is a dependent, is a response. It's also the target. So the question says that if you are having this target in front of you, which two variables are highly correlated with this target variable? Young.
Doc, price and price of complement.
Give me the first pair.
The price and the quantity demanded, sir.
And I mentioned the numbers.
0.87.
Next.
Minus 0.87.
Yan.
Yes, Doc.
Which is the next pair?
The next pair is the price of complement and quantity demanded.
Number.
0.74.
Very good. I said two pairs, so you've mentioned two pairs. That's perfect.
Thank
That's
you,
what I hear. It's a class rep here. Jan, your hand is still up. Yeah, Samuel, go ahead.
Please, the next pair is the quantity demanded and then the price of the complement good, which is 0.72.
Good. You should be able to identify that. And then you say, what does that tell you in terms of the predictive potential? It means that price is the one that is probably likely to do more because price is significant. It's actually the most significant. I always don't say that it's significant, it's good, but also try and find the money, what do you call it? Saying that is significant. Try and find a potential power. It's predictive power in predicting the dependent variable, in predicting the target. Okay. More importantly, you got to check whether they are significant. Now, if you want to know whether they are significant, you have to use the stars. 3 stars means they are significant at what percent? 3 stars. It means they are significant at what percent? Mm-hmm. 3 stars.
5%.
The fact that it's taking you long means you don't know. So whatever you say is a guess. And I win.
Prof, please, is it 1%?
Are you asking me or telling me?
Less than 0.01.
What about 2 stars?
Prof, 2 stars, 5%.
And what about 1 star?
1 star, 10%.
You see, you guys should know that I also you can specify. See, so here I've specified that 1% is 3 star, 5% is 2, 10% is 3. Those are the errors. Those are the errors you actually make in a risk. So looking at our own, which ones are significant? Guys, hold on. Let me just collect your IA script downstairs. And the one you do in week 6. Just a second. Think about this. Just give me 2 minutes. And think about the next sort of question on your screen. I'm coming.
Hello guys, can you hear me? I don't
Loud and
think.
clear.
Okay, thank you. Thank you for your energy. And those of you who aid me. So what's the answer? Someone should tell me so that I see it, and then it's like, oh, you guys, you contribute in class, and then yeah, I can get an extra mark. Okay.
Hey, colleagues who are not on the call, I'm taking pictures of all those who are not on the call. Okay, which two pairs of variables may be mostly multicollinear? Guys, did you do multicollinearity?
Yeah.
Good. What is it about? So just on top of your head, what is multicollinearity?
Strong
don't know.
relationship.
If you don't know, then I define it for you. Should I define?
Yes, Lord.
I think a strong relationship among the features, but not the target itself. Strong
Yeah,
relationship
that's
among
good.
features.
You have some ideas. You have some ideas. Obed.
There are two variables which are related to each other closely, but not in relation with the target variable.
So they can't just be two variables. They have to be two independent variables. So multicollinearity exists when two independent variables are so highly correlated. Two features are so highly correlated that it becomes difficult to disentangle the partial effect. It becomes difficult to disentangle the partial effect of one from the other on the dependent variable. So their relative position or their relative net effect on the dependent variable is missing. And they have to be independent factors. So looking at the ones we have here, which variable would you say is the first most multicollinear pair? Obed.
Doug, please, price of the good and then the price of other complement good.
Good. What is the coefficient?
0.74.
Wrong. What is the coefficient?
Negative 0.74.
Correct.
Fucking.
I'm just showing you the marking scheme. If you had said that in an exam, you would have failed. So that's it. Okay, that's the first pair. And the next pair, you can detect the next pair as well. So these are correlations. Guys, you should know everything that we have said regarding correlation and also regarding multicollinearity. But please note that multicollinearity that we just said, well, the example you gave is just a guess. It's just a guess. If you want to do proper multicollinearity check, that one, you can't do this. So you have to use something else. And what is that? You have to use something known as variance inflation factor. Were you taught variance inflation factor? No? The variance inflation factor will tell you whether the correlation, that particular variable is multico or is not multico. You need to calculate the VIF of every variable. Let me just flag that you can also do a scatter plot of the data set to simply know the relationships. So just look at the first one. The first one is price, which is here. And the scatter plot for that, if you check carefully, okay, the scatter plot for that, price with quantity, if you check the graph carefully, what relationship is it exhibiting? The one I'm showing, what relationship is it exhibiting carefully? Anybody? What relationship is this? Abdul Salim Hassan.
Negative relationship.
Negative. What about complement price? This one with quantity, what is it exhibiting? Abdul. Nene.
Positive relationship.
Positive. So you see this scatter plot using using the what do you call it, the C-bend can help you to be able to determine the situation. Of course, it's from that we actually went to doing things. So now that we've been able to do correlation, we can now proceed to do what is known as regression. And this is a masterpiece. Today, I'm not going to teach you practical. I'm just going to teach you the theory. There are several kinds of regressions that you can do. A regression where you have one dependent variable or one predictor and then one target. And that is simple regression. What is the difference between simple regression and multiple regression? Who can tell us? What is the difference? Simple and multiple. Simple and multiple. Simple and multiple. What's the difference? Jonathan. Haruna.
Hello. So I think simple regression has just one predictor and one outcome. And multiple has one or more, two or more predictors, but one outcome or one target variable.
When the outcome or the target is more than one or more than two, what is that? What is that? When the outcome or the target is more, what is that? Limited dependent variable regression. Limited dependent variable regression. Limited dependent variable regression. Take note. And there are quite a number of them. Some of them are basically two and just two. They are the logistic or binary classification. Just two. But we also have other ones like censored, probit. You can have truncated. See, just two means 0 and 1, but you can also have 0 to 1. 0 to 1 is different from 0 and 1. 0 to 1 is a fractional systems regression. So fractional response regression. You get to know all of this, particularly, this semester you get to know them. And then when you are doing applications of AI, you will learn them even more. Okay. Please note something. There is a polynomial regression. What makes it polynomial? Sometimes it's known as nonlinear or quadratic. What makes it polynomial? It is the fact that one of the independent variables or one of the features has been squared. When you square or you cube, we are now in the world of nonlinear regression. I'll teach you this forcefully. When you square and you cube. But the question is that why would you want to square something or cube something? Why would you have something like age and then you square it? Why would you have that? Well, I know why. Okay. I know why you will have that sort of thing. You will have that sort of thing because sometimes you believe that that variable rises and eventually falls, or it falls and eventually rises. Guys, are you with me? Are you with me? Are you with me? Are you with me?
Yes, sir.
Can you give me an example of something that is rising and eventually somehow it starts falling? In other words, it will exhibit diminishing marginal returns. One example is the experience of footballers. When a footballer starts and as his experience is going up, it keeps rising. So the number of goals and the performance is increasing. But it will get to a point, what will happen? It gets to a point, what happens? Even though he is getting more experience by age, that experience is not helping him because he's not able to score the way he's supposed to score. That is when they start going to Saudi Arabia to go and make money. So in this case, their impacts have exhibited or have entered into the zone known as diminishing marginal returns to the target outcome or the outcome. That's a football example. Another example is a company size. The size of a company is determined by the total asset. And when a company starts, like Ghana Commercial Bank, the size will be small. Then it start increasing, many branches, many customers, many branches, many customers. Over time, it becomes so big. And when it was becoming big, profit was going up. But now it gets so big, then profit still starts coming down. Why? Because people are lazy, some are not working. Take, for example, the ministries. The ministries, because it is choked with so many workers, people don't do well. They are not efficient. They check. The word check here means that somebody thinks somebody will do the job, so nobody does the job. And so if you believe that something like this is happening in your model, then you have to introduce a square of that variable. Sometimes you even want to introduce a cube, a cube, because you believe that a thing will rise, it will fall, then it will rise again. Well, if you have proof of that, you should introduce that. So that is a very important point for nonlinear regression. Sometimes you have something called multiplication of some of the independent variables. This is called interaction effect. So you believe that there is a relationship between experience and that of education. They match together because some people, they have to go and get experience. After the experience, then they go and get education again. But your education you are going to get, they will ask you that, do you have at least 2 years of experience? So if you don't have 2 years of experience, you cannot go through that education. So you can see that the two of them are related before they affect the salary. So if salary goes up after the degree and the master's, and then the manager says, so your salary has gone up because you have had master's. But he said, no, my salary went up also because I have 2 years experience, which means the two of them are fighting together to influence the Y. And that is a typical example of interaction factors. So you can have interaction factors like X1, let me show you something, X1, and then X2, then you multiply the two of them. So at first you had X1, then you have 20, you have 30, and so forth. Then you have X2, which is 15, 14, and so forth. Then you now have X1, X2. Okay, where you multiply the 20 by the 15, you multiply the 30 by the 14, you create a new variable. And then you try and see whether that variable jointly, they will have a multiplicative effect instead of just an additive effect. You will have a multiplicative effect on the dependent variable. So in this case, your dependent variable will be wage or your salary. And your salary will be a function of all of these X variables. So these are all possibilities of regression, even at the basic level that you need to know. We'll finish in some few minutes time now. Now, there is always a difference between a specified regression model and an estimated regression equation. Do you remember we did this thing the last time? So this is a typical example. In fact, in your long essay, you have to write models like this. Okay, you got to write models like this. You talk with your supervisor, you got to write. Okay, so you can see that the wage have got two things. One is a specified model. The other is the estimated equation. The estimated equation has no error term, and it also has numerical values, coefficients. The specified regression model That one has beta parameters and an error term. So you should know the difference a lot. You should know the difference. If I were to do prediction, which one do you think I will use? The specified model or the estimated regression? Which one do you think I would have used for prediction? The specified or the estimated?
The estimated.
Good, the estimated. That's what you're going to use to do your judgment, because estimated has numbers which can be used for further work. However, before you can do any regression, you need assumptions. What are assumptions? Assumptions are certain things that must be in place for certain things to work. The moment I say the University of Ghana is running, we have already assumed what? Tell me one. Before I say the University of Ghana is running, then we have already assumed that they are lecturers and they are teachers. So assumptions are very, very important. And in regression, you need to buy the assumptions. If you don't make the assumptions precise and concise, people will start doubting what you said you have. They will doubt. So go through the assumptions together. Linearity, normality, independence, homoscedasticity, no high correlation, no autocorrelation, no specification bias. Understand these assumptions and ask in the page, can somebody please explain this assumption well for me? Remember, you have a limited time, so you want to learn as much as you can. Okay. Next time, we are going to look at other things that you need to question before you undertake a simple and multiple regression. Okay, there are about 20 different questions you got to ask yourself. We'll look at that. We'll look at standardization and several things. We'll look at what do you call it? Yes, we'll look at standardization, feature scaling. And then we'll also look at training a model. How do you train? What is the essence of even training the model? We'll look at all of that. Ladies and gentlemen, that brings us to the end of the entire caboodle. If you have a question, you can ask. If you don't have, enjoy the rest of your weekend. Until we meet again, have a wonderful weekend. Bye-bye.